All right, everybody. Hello. Back for another weekend, I guess, with me, or for at least an hour or so. Um, everybody, say hi in the chat so I know who I'm talking to. That's always handy and helpful for me. So yeah. We'll give folks a few more minutes to join, bring up some of the prepared material I have. Not exactly sure where this one is going to go because, well, yeah, this is a fairly large subject and can be pretty open-ended. So yeah. Hey, Jack. Hey, Rainer. Hopefully we've got a good one planned today. I think it's a good one, but I might be biased. You shut off some windows that might be distracting here. You can see that I went back in history here and pulled up a oldie but goodie data sheet. Hey, Daniel. 100% attendance award goes to Daniel. That's, hey, Marco. Whoops. Alexa's about to play something here. Hold on. Benjamin, yes, these will be recorded and available after everything is done. So if you can't stay for the whole thing, it'll be there. It'll be there. So yeah, we'll give folks a few more minutes. Yeah. I didn't even think I said something that resembled the keyword there. We're lucky that the mixer is at a fairly low volume level at this point because last week I nearly took out some people's eardrums by playing some horn subs, and I only have about 30,000 watts behind that audio system sitting there. It's good for relaxing ambient new age sounds. That's what I listen to with it. Ocean background noises. That's incredibly realistic. It's good stuff. Good stuff. Wow, we've got Malaysia and Chechnya. This is awesome. I love the internet for this. This is crazy. All right, well, we'll give it another minute or so for people to hop on, and then we'll go ahead and get started. Everybody, say hello so I know who I'm talking to. And if you have questions, please, I'm hoping that this one, and I'll say it again multiple times, I'm hoping that this one is very foundation rattling ambient. Yes, foundation rattling. As I said in the last video, I've had drywall come off the ceiling. I've had things fall off of shelves in different rooms. So yeah, good times. I'm hoping this one is very interactive. I would like lots of questions. This one is, as I said, I'm going back to a sort of a more basic topic than a couple of the previous videos. But that doesn't mean that there's not a lot of material. It's a lot of foundational material if you're going to do speaker design, and as a result, there's a lot of really critical stuff in there. So hopefully we'll and India. This is amazing. This is so cool. I mean, like, I know how the internet works. I've only been an electrical engineer now for like 25 years, but it's still cool. Like, it's just cool to me. So yeah. So, all right. Well, it is 12:05, so we might as well get started. And I will say this. Last time I was on a video and talking about teal small parameters, I kept pronouncing it feel, which is incorrect, and Andrew Jones corrected me. I do not wish to be corrected again, so I'm just and I've only said it the wrong way for since I was probably 13 or 14, and so it's a very hard thing for me to undo. So we're just gonna go with parameters. That's a good cheat for me. Hey David. Hey Greg. This is awesome. So we're gonna go with parameters because that way I don't have to mispronounce anybody's name. I have on the screen here pulled up a data sheet from an older woofer. This woofer is still made. It is currently made in a slightly different part number by ScanSpeak. I think over the years they've had to slightly change possibly some formulations of some soft parts because the newest ones have a slightly different response. That may also very well be due to improved and or just different measurements. You have to always kind of keep that in mind. And this woofer is sort of a classic. If you did speaker design, frankly, in the early 2000s, late 90s, you used this woofer. I went to CES a couple of times and sort of wandered the high-end halls, and if I had, $10 for every time I saw a design using one of these drivers or its 5-inch cousin, the P13 driver. Yes, small signal parameters. Boom. If last time I had an actual boom in the video, so we won't do that. If I had $5-10 for every time I saw one of those drivers in a speaker at the high-end CES, I'd be able to afford the flight home. They were very, very popular, and for good reason. They were great woofers. These days, I think technology has sort of moved past them, but it is a great way to sort of look at a older spec sheet. It is sort of a great way to look at the parameters that we are interested in and things like that. The other one that I've got pulled up is another sort of oldie but goodie, the Seas P17RE. I used this one as well. In fact, these were basically direct competitors for each other for a while. And we're going to be putting some of these in. Again, we're going to sort of compare these data sheets and put them into the vented box modeling, although this can do several other types of boxes software that I'm going to be using for this demo called Basta. It is freeware. When you download it, keep in mind, whoops, I got too many curves on. Keep in mind when you download it that there's a serial number that you got to put in, and you have to run the program the first time and create some background preferences files and stuff like that. So you've got to run it as administrator the first time you run it, otherwise it just starts and stops. So we're going to go back to this P17WG, this VIFA, and talk about sort of how far loudspeaker design has come in a lot of ways, and then put this into Basta, and then take a look at some of the curves that you can get. So when you look at one of these spec sheets, if you're new to speaker design, this spec sheet looks really imposing. It has a lot of stuff on it, and you might think that this is more than enough information to design the complete speaker. That is not true. There's not near enough information on this spec sheet to design a complete speaker. You have to do a lot more. You have to take measurements for frequency response, things like that. What there is enough information here is to sort of make some judgments on things you might want to watch out for in your speaker design and model the low frequency performance of this driver in a box. So, yes, Rainer, Basta is free. Basta is free. In fact, do a Google search for Tolvan data. In fact, tolvan.com. That's where you get it. Okay. And here's that line I was talking about with known issue. There are other programs. In fact, on DIYRM on my page, I compared five different modeling packages to show how they're all slightly different because they all have slightly different models going on in the background, slightly different math going on in the background. But this is free. I like this one a lot. It seems to be fairly accurate for me. It does a pretty good job, and I'll talk about where it sort of starts to break down compared to some of the other ones, and just in general where all of these start to break down later on in the video. I have measurements and stuff that I've taken and all sorts of cool stuff, so we'll get there. Daniel, I had no idea. I learned something new today. I'm done. I'm done. I'm quitting the presentation. 12-ish. I'm quitting the presentation because I learned something. Oh, well, he's got 12 sitting up there. 12 and data XII. All right. Anyway, so yes, it is free. So let's go back to this woofer. What are the sorts of things that you can tell from the data sheet? Okay. You can get an approximate idea of where you're going to be able to use this driver up to before you're going to have to start worrying about a crossover. Okay. Only approximate. Things happen when you put drivers on baffles, and baffle step kicks in, and it depends on exactly how bad those breakup modes are, and things like how repeatable those breakup modes are. For instance, years ago, I used some of the Seos Excel magnesium coned woofers, and they have a very pronounced breakup, and I used them over a couple of years, and they were extraordinarily uniform in their breakup characteristics. The quality control on the cones for uniformity year to year was amazing. Conversely, I've used some Kevlar drivers that sort of production batch to production batch. That breakup mode is really wonky. This driver is really smooth. Like, this is a very smooth roll off. So that tells me that I probably won't have to pay extra attention to this upper range in the crossover. I might still once I see it in a measurement, but that's about it. That's about all that I look at when I see these frequency responses. I look to see if this gets really wild up at the top end. I look to see, like, for instance, this one shows a little bit of baffle step here in the anechoic chamber of whatever size test baffle that they have. Same thing for this Seos woofer. In fact, somewhere on here, they used to say, this data sheet may not have it. Oh, yeah, they did. 12-liter volume enclosure, right? So that's why it's FS in the measurement, and they flipped it upside down for you. It makes it handy. Is higher than the free air FS, but that just tells you that they had this thing measured in a box, or put in a box for the anechoic measurements that they have. Okay. Conversely, we won't pull that up. The next thing that I look at is these small signal parameters, these teal small parameters. This is I did it again. These are what you use and you put into the modeling software to build a computer model to see what the low frequency response of your speaker is going to be. Okay. It is an entirely different presentation to go in and explain what each of them is and sort of how they relate to mechanical constants and mechanical things in the driver. And I'm not going to be able to get into that today. I wish I had some time for that, but I don't because I've got too much other stuff. So what do I sort of key in on when I look at these? Well, honestly, the very first thing I look at is Xmax. This tells me how far the cone is going to move, and I'm going to use huge air quotes here. It's how far the cone is going to move and be quote-unquote linear, okay? Because even within quote-unquote linear Xmax, I have still seen some interesting things, okay? So this is an older technology driver, and they don't actually give you Xmax, which is handy, right? That's because back in these days with when this driver was developed, relatively few drivers had sort of these fancier motor structures. They had a flat top plate and a pole piece, and the pole piece might be extended, it might not, it might be T-cut, it might not. Only the expensive drivers like the Scanspeaks had the shorting rings and the motor structures and stuff like that, right? And so you would be expected on this spec sheet to realize to put in an Xmax of 3 millimeters one way, 6 millimeters two ways, based on the voice coil height and air gap height. And that's a reasonable approximation, okay? I don't know if, let's see, does the SEAS sheet here? Yes. And so same thing for this SEAS woofer. This one actually says it. They also give you, on this woofer, they give you a maximum coil travel. Linear is, again, air quotes, linear is the region which it'll maintain those parameters-ish. Maximum is the most it'll go before you start breaking things, like seriously breaking things. What data sheets don't tell you is when you exceed that, what happens, right? You can make a driver where if it exceeds that in the back range, the voice coil hits the back of the back plate, and you can almost be assured that you're going to break the driver very, very quickly if that happens enough times and hard enough, right? The drivers don't last very long when you do that. You don't know if it's going to hit soft parts on frames. There are actually drivers that are designed so that the soft part, like a spider or something, will hit part of the frame. The driver will come to a stop, but you're not hitting hard thing to hard thing, and you're not shattering stuff or rolling voice coils over and things like that. All of which, in various testing scenarios, I have done. And so I've actually even had drivers jump the gap in the forward direction where they come completely out and the voice coil gets off-centered and then they get stuck on the out position. Then you can sort of shift them back in and get them to work again, but you don't know if you've put like little micro tears in the surrounds and the spiders and stuff like that. So you don't know if you've broken it or not unless you have like a clipple and you can go find those things. So I look at Xmax, I look at power handling, and then after that, I start to look at some of these other parameters, okay? For years, I have seen people say, well, if it's a QTS, total Q, of 0.4 or over, or 0.5 or over, it should be in a sealed box. Or if it's under this, or they'll sometimes use a product called EBP, Efficiency Bandwidth Product, for making that determination. I ignore that completely now. I literally don't care. I will put it into the simulation software and see if it gets me the response I want in the box size that I have available to play with. I ignore that completely at this point because I have done like my Iridium 2 design. I think that woofer has a QTS of 0.5, but I put it in a vented box. I have on many occasions used like a QTS 0.2 for a mid-range and put it in a sealed box. So the application matters more than the individual parameter, and you need to sort of keep that in mind. Okay, so we're gonna put this driver, and I've already done it, but I'll do it again. I gotta find my mouse though. We're gonna put this driver into the Basta software. And let me make sure that where I'm putting everything is not hidden by, in fact, you know what we're going to do here? We are going to make me go away. Haha. Nobody wants to look at me anyway. All right. So, when you come up, when you bring up Basta, I've just clicked New System. You've got some inputs here for the box size, the vent, and you click on these to bring up the area that you want to put it in. Okay. This particular driver, as I said, since they don't give me Xmax, we're going to put it in there. So I'm going to make this driver now. This is the P17WG0-00-06. It has an FS, a resonant frequency of, where is it? 35 hertz. Well, that was lucky. And what you have to do is you have to enter the things that are checked. It will calculate the unchecked things for you. And if you change these checked things, it will, like you have some of these parameters, but you don't have others, it will calculate the others for you. If you enter something super, super wrong, like VAS, equivalent air volume of 1,000 liters for this driver, which is ridiculous, right? It tells you that this red tells you that this can't happen. Like this is physically impossible. So you can use this to sort of check the driver manufacturer's sanity level and see if they have lied to you for these small signal parameters, right? And sometimes they do. Cough, cough. The auto driver manufacturers do this all the time. Just saying. I see it more with them than almost anybody else. I'm not going to name names, but they're relatively easy to find. So let's go back and put the actual VAS in there. 49.4 SD of where is it? Should be effective cone area. There it is, 136. You do have to sort of be able to figure out, you know, how these cross over with each other. BL of a whopping 4.1. I am so used to using Pro Sound drivers at this point. The BL of 4.1 seems anemic. This thing has no motor strength. RE, where is it? Should be in the voice coil resistance. Where is it? 4 ohms. QES, we don't have to enter. QTS 0.4. Okay, so now we can go in and we can sort of double check here. QES, it calculated as 0.575. Now, once you get past this sort of hundredths place, this is sort of silly, but numerically it calculates it, right? It gets all the way out to 0.575. So that rounds up to 0.58. And what does VIFA have? 0.58. All right. QMS of 1 something, 1.3, 1.3. Yeah. Okay. So, I basically believe most of this stuff. Right. LE. What is the LE equivalent inductance? Does it give it to you? 0.4. Okay. Now, LE loss. Last time for horn response, I went over lossy LE, which is this sort of BL reduction thing. LE loss, in this case, is more of the semi-inductance modeling. For most drivers, just leave this at the default of 0.7, okay? There's a technical data thing that you can download from their website that goes into that. But that is more of a semi-impedance or semi-inductance impedance model, and it's fairly accurate. 4 millimeter or 3 millimeter Xmax and maximum power, nominal power of 50 watts. So I have now put this speaker into Basta. Okay, so you can save a driver file. I already have it, but I'll save it over it. And now we can go design a box around this. Are there any questions so far? Any questions that I've got so far? Right. I'll keep going, and I'm back where I can see the comments here on this screen. So if anybody has any questions, feel free to put them in there, and then I will put me back on the screen because we're not going to be looking at the. All right, so we're going to go one of the things you can have Basta do for you is have a design suggestion. Again, there are some programs that will give you a lot of sort of alignment options here. I remember a long time ago, it was very popular to make sure that your vented box for a residential bookshelf or tower type speaker to be QB3, Quasi Butterworth 3. Much like the rules of thumb on vented versus sealed enclosures, I completely ignore those now. I don't pay any attention to them. I go based on sort of F3 response shape, max output, and power handling because I have found that well, we'll get into that later, but remind me to get back to that. So it'll give you design suggestions here, right? And you can literally just say apply. Whoops, I just applied it to the wrong thing. You can say apply, and it will give you that box. Now, there are some things to watch out for here because it has some defaults in here that you may or may not realize, okay? And it will give you, you can also pick different formulas like there's this Ullman one, there's a Keel, there's one that's pretty good. And if I change these, you can see where they give you slightly different answers, but not, the response doesn't change so gigantically that you go, oh man, that's what I want to do or not, right? Like you'll have to take a deeper look at any of these. So go back to this one. I have no idea. That kind of looks like a QB3-ish like thing, but whatever. You can then pick a whole bunch of different curves, okay? Don't get like overloaded by this. There's a lot of these that are not necessarily something you're going to use unless you have a very specific application in mind, okay? I actually often turn off the electrical impedance one so that I don't have to look at it. It kind of confuses the plot for me at first. I will often turn off the vent response because I don't know if I really care. I'm looking at this point at the overall system response. And I will often turn off the driver response, okay? Because again, I don't care. I'm again looking at the total system response. A lot of times I will turn on cone excursion because that is important to me. Okay. I will also turn on maximum output level. Okay. And I will turn on vent excursion or vent velocity. There it is. Okay. These to me are more useful things than the default impedance curve and stuff like that because these are parameters that mean something in real life that if I start to go past certain numbers, bad things happen, right? Remember when I talked about that maximum excursion plot or parameter that VIFA gave you, or that SAS gave you? That's if I start to exceed that, right? And we can certainly do that in the model. We can certainly put inputs into this model that mean we will go blowing right on past something that you could physically do. That's a definite don't. In the do's and don'ts category, that's a definite don't, right? The model's not accurate up there. So these are handy to me. So if I were sort of a new speaker designer, I might get really excited by the fact that this system has a, let's see, 90 decibels. Where is it? About 87. That this system has an F3 3 dB down point of like 34, 35 hertz. Okay. And I'd say, oh, I've just designed a bookshelf speaker that gets to 34 or 35 hertz. You really haven't. Okay. This is where that maximum output level comes in handy. Okay. So what goes into this? Okay. Maximum output is determined by vent velocity and driver power. Okay. And if you look, if I click on that and say at 30 hertz, my maximum, or 35 hertz, my maximum output level is 84 decibels. That's really, frankly, just not that loud. All right, at 30 hertz, that's just not that loud. If we look up the Fletcher or 35 hertz, in fact, let's do that. Fletcher Munson curve equal loudness contours. The threshold for audibility at 10, 20, 35 hertz, right, is 60-ish dB. So you've only really got like 25 dB of audible range before you've hit maximum, right? So, by the way, that's what that curve is used for. Not your speaker design. Not your frequency response of your speaker. So yeah, that is something to watch, right? What can we do about that? What can we do to get our maximum output better? Well, what could be limiting it, right? Is it excursion limited? Is it the velocity of the port? Well, let's go into Basta and go into Vent, and let's see what we've got. Well, first off, the speaker is tuned to 36, 37-ish hertz, right? With a 2-inch diameter port, or a 50 millimeter diameter port. That's tiny. That's kind of tiny, all right? The other thing is that the defaults for Basta is that the max port velocity is 10 meters per second. I've done a lot of experimenting on this. A lot of people have 17 meters per second for a round port of reasonable geometry, sort of in that 2 to 5 inch diameter range. Once you start getting bigger than that, I think the chuffing numbers and the Reynolds numbers and stuff like that, the audibility of that start to break down a wee bit because of I'll get into that later. So I'm going to type 17 meters per second here and click, and lo and behold, my max output changes. Okay. I'm going to go back to the 10. Watch this. See how this right in this area? This is where the port is output is important. So that is was our limiter, or one of our limiters. Okay. Now let's for experiment purposes, let's go back to that driver and say that we can put 500 watts into it. We can. We'll blow it up, right? Does the max output down here change? No. Okay. So that truly is the port limitation. Now the max output way up here went way up, but that's not realistic. If we did that for any length of time, you'd burn that driver up. Again, I've never done that with that particular driver. I have on others. So we'll put this back to 50. Okay. So again, as I've said, I look at this curve far less than I look at this maximum curve. In fact, let me change its appearance so that I sort of, there we go. I look at this one a lot more than I look at this. As long as this shape is reasonable-ish, right? As long as it doesn't have a huge peak to it or something like that. A lot of times with room placement and things like that, you can get a pretty good response that you're happy with out of. But if the speaker won't put out enough energy into the room, if its output isn't stout enough for your listening purposes, you're not necessarily going to be all that happy with it. And so I have found I pay far more attention to this. Okay. Let's see. So what I have done is, let's see, where do I want to go next? Any questions? Let me go back to that screen. I may have like 5 questions and not paying attention. Okay, no questions. But we're not losing audience members yet, so this is good. Thank you, folks. So I look at those. Okay, that curve to me is the most critical. What else do I look at? Okay, I said cone excursion, right? Okay, so let's do something here where I change the input power. Okay, where is it? Power amplifier. No, that's not it. Source. So I've got 2.83 volts. That's the nominal voltage for sensitivity. What if and 1 watt nominally into 8 ohms, which the speaker is never, I mean, it's like 8 ohms in 2 spots, maybe 3. I'm going to change this to 28.3. Okay. So now look at my charts. And one of the things that you need to do with Basta is to remember that you can change your scales by clicking and dragging them. It takes a little bit getting used to. Okay. So when I change this to 28.3, if I was using any other program and I wasn't using their sort of versions of this maximum output, and most of them have some sort of version of that, I would say that that was my response. It is not going to be your response in real life. It is absolutely not going to be your response in real life. Why, right? Okay, let's look at our vent velocity. I am up at, with those vents, 64 meters per second. That can't happen, okay? Starting at about 30, 35 meters per second, the vent will actually, the turbulence in the vent gets to be so high that the vent actually starts to close over, and it becomes the air. You can't shove the air through it fast enough. And so you end up with a lot of noise coming out of that vent, whereas 17 meters per second for a round vent is sort of the onset of audibility of chuffing. At 30 meters per second, that thing is huffing and puffing, and it's going to make a god-awful sound. A roadmap, I don't have a roadmap on these things. That would require prep and time. Sorry. After this, we're going to go over, I've got some examples where I measure an actual speaker and show you how accurate some of these models really are. Okay. So that's what I have after this. What is the other thing that we can look at? Cone Excursion. I have got this driver supposedly going up at 10 millimeters one way, above the resonant frequency, and down low, it's up close to 50. That can't happen either, right? We'll break the driver. So even though these drivers were put into systems where people would give them 100, 150 watt ratings, if you actually use them up there for any length of time, more than just a sort of a dynamic transient at higher frequencies, you would break this driver, okay? This is a definite don't in vented box modeling. You have to pay attention to make sure that your vent speed is under that 17 meters per second if you want these models to be at all accurate. And you have to make sure that the excursion is under the limits in the data sheet, okay? And as I said before, even then I've seen some weird things happen, especially with really huge vents and really large PA drivers, like 18-inch woofers where the vent size is over half of the SD of the cone, right? So you've got like this 1,200 centimeter square cone, and you've got a 700 square centimeter port, right? I have seen some deviations from these models because these models weren't designed with those sorts of aspect ratios and backing or those sort of aspect ratios and that sort of physics behind it, right? They were designed for when speaker drivers had 40 watts of power handling or 50 watts of power handling and 3 millimeter Xmax, right? So let's see. I'm going to take us off of the power amplifier. Where's source? 2.83 volts. Okay. Now we're back into the realm of possibility. So next I'm going to go to a box that I actually built and designed. I haven't on this one. I'm going to go, in fact, we're going to turn this one off. We're going to turn this one on. Okay. And I've still got driver response, vent response, velocity, electrical impedance. We're going to take off electrical impedance. Okay, so this is the Vital Pro. This is a box for the Vital Pro 8RS250. It's a it's kind of a beast of a woofer. I was trying to find the clipable files for it earlier, but I was not able to. If I pull up the Vital Pro 8RS250, you can see a picture of it here. It is made by the Pro Sound company, Vital Pro, but it's sort of in this. I doubt you'd use it for true PA. You may use it for studio monitors or even stage monitors, or sort of like fills for bars, restaurants, and stuff like that. But it doesn't quite have the sensitivity that you'd want for like actually trying to cover a large audience, right? It is a 200 watt power handling jobby. Its X-Max they list at almost 7 millimeters. They call maximum mechanical excursion what it should be called, which is X damage, where you're going to break it. And that's at 16 millimeters. And so, so this is a speaker that I've actually built, and I've done some measurements on. So let's take a look at this one. All right. There is, and I promised somebody earlier in the week that I'd get to this. They kept talking about not being able to fit vents in boxes. Okay, and this woofer is a pretty good example of it. It's very easy to design a box for this woofer that the port is too long. And one of the ways that you get around that is you go with passive radiators. Well, that is typically only used in home systems and sometimes in cars. I've seen it in cars. In Pro Sound world, you just don't see them for a couple of reasons, cost and other reasons like destroying them. Nothing suitable to use. And so let's talk about why that is with modern woofers versus sort of the older things that were around when the small signal parameters models was developed, right? It has to do with power handling, okay? If I look at the output of the driver, it hits its minimum, okay, at the maximum output of the port. In fact, you can find your tuning frequency very, very precisely if you near field the woofer, and you look for that minimum. It's actually easier to find than finding the peak of the port output, right? Well, if you've got a system where the woofer is at a minimum in output, that means it's at a minimum of movement, okay? So it doesn't matter how far the woofer is, it just matters how much power you can put into it, and it will activate that resonant system, and you can overload the port, okay? That's why, you know, like a 30 watt or 40 watt Audax HM170Z0 versus a 100 watt SB 6-inch woofer, right? It's tough to have a port that can handle the full output of these woofers. And you get into the Pro Sound world and you get these 12-inch woofers with 3-inch X-Max but 1,000 watt power handling, and every single one of those boxes is underported, right? Like you just can't make a port work well enough for those drivers. So if I went to measure this response, this black line, let me turn off the driver response and the vent response, okay? If I went to measure this, I would never get this, okay? I would never get this response. And the reason is that this response assumes that you've got the woofer in half space. It's buried flush in the ground, and there's this infinite baffle going forever and ever, even though the box is a certain size, okay? Basta can simulate baffle step and show you what you'll typically actual measure. So what I did is I did the Baffle Designer, and I put in my baffle that I've actually built, and I have 2 ports on this one, and the 8-inch woofer on a box that's roughly 12-inch square. And right now I've got baffle step disabled, but I'm going to enable it. And let's see how the response changes when I do that. Okay, in fact, you know what I'm going to do? I'm going to copy it, and on the copy, I'm going to disable. Okay. So now you can see the difference in the responses because of that baffle step. where the driver can acoustically see that baffle. And I'm on the wrong screen to not see any questions. I apologize. Let's see. Scott, didn't I bury a woofer in the ground? I have done that. I have buried drivers. Actually, it was a tweeter most recently because I was trying to eliminate the baffle. When I talk about measuring speakers, everybody says bury it in the ground. That's how you measure it, and that's a great way to measure the driver. That is a lousy way to measure the speaker. Okay, and it shouldn't be done if you're looking at the completed speaker. I did it for the horn diffraction paper that I put out. And it was a very hot day, and I sweat a lot. And I almost destroyed the tweeter because I kept sweating onto the baffle, and I was afraid of getting the tweeter soaking wet. They say they're waterproof. I don't know if the tweeters, at least that tweeter was waterproof, but I didn't know if it was sweatproof. And years ago, I did it for to prove to myself that I understood the baffle step and sort of the ground plane versus baffle step versus gated measurement differences properly. And I'll never do it again. Now that I've done that for a full speaker once, I'm never going to do it again. We have way too much granite and stuff like that in the ground here. You get about 6 inches down and clunk. Or if you don't have granite, you've got clay where I am. So you get about 6 inches down, and then you have to like use a spatula to get the dirt off the shovel. Let's see. Same true for aperiodic or passive radiators. Let me get back to aperiodic. They're different. Let me get back to that. And if I don't get to it in this video, maybe I'll do a paper on those because they're special and unique and a neat little snowflake and very different. And I've done them, and they're great. It's just they're hard to get. I think they're hard to get right, but I'll get back to that. Maybe. So you'll never get this response, this sort of flatter response. You'll actually measure this response. So I actually went yesterday, and for this presentation, in fact, let me take the non-baffle step off. For the presentation, I went and measured ground plane. Not buried, ground plane, where I have the speaker on the ground, the microphone on the ground, but I put the microphone at 2 meters so that it comes back. I went and measured this box that I built. Okay, let me find that. And you're going to have a lot of curves. I apologize for all the curves. And here's what I got. Okay, now there's a lot going on here, and I don't want this to really flip people out. But here's what's going on. I measured the box without any stuffing in it. Okay, so there is a port resonance that is extraordinarily audible. A first order pipe organ resonance that is extraordinarily audible. Okay, and that is shown sort of in, let's see what happens, in this range right here, where you've got this dip. That's where that is. Now it goes away if I properly stuff the box. Okay, but this box wasn't stuffed. Okay, and what I did is I measured this at 2.83 volts, and then I started stepping it up. So these curves here, and I'm hesitant to, we'll do it. Clear selections. No. I shouldn't have done that. No, I shouldn't have done that. Okay. So here is the agreement that I got. Okay. That's not bad. Okay. I'm here to tell you that's pretty good. Okay. I've got a 3-story apartment building next to me. My house is 2 stories. I've got a big fence behind me. So I don't, at super, super low frequencies down below 40, 50 hertz, those structures start to impact your measurement, but you can see how good the agreement actually is. Okay. And you can see that as I step this up, in level, the agreement hangs tight, right? Like it is good, okay? Now, I didn't actually drive this thing into non-linearity because my neighbors hated me enough already. These are not exactly quiet sweeps. But I wanted to show you something here, okay? The highest level that I drove this thing at was 16 volts RMS for the sweep. And I wanted to show you something when we go back to Basta, okay? So, source, 16 volts. Why didn't I change it? Why didn't I change it? Change it. Come on. Oh, I'm on the wrong one. That's why. Live demos. Live demos. We're going to do this one because that's got the baffle step. 16 volts. Look at what we've got here. Notice how it's got this maximum output curve determined by the power rating of the woofer and 17 meters per second in that port. Notice how the system response stays under it. Okay. That agrees very well with what we saw here. I have no doubt that if I went to 32 volts and tried to model it, right? This is, again, a don't for the software. I can put 32 volts in here. And there's some really advanced software that will actually start to show you this difference, right? But if I had to put 32 volts, see how it kept the shape the same? That wouldn't have been the case, okay? So that's a don't. Don't believe the software if you've put in such a high voltage that you've exceeded either Xmax or that 17 meters per second on the woofer, okay? What else? What else? Do I have any other questions? Again, I'm off this window. I want to ask something. Would love to have a video on the ground plane. That is going to happen. That will happen. I have to wait until we've had... that's going to have to be a nice weather day. I know it's October, but it's... what is it in C outside right now? 100. It is 30, almost 38 degrees Celsius outside right now where I live. So we're not going to do that outside today because all you would see is just sweat pouring down my face. Let's see. I wanted to ask you something. Do you design the vented box while looking at the electrical? What happens when your box had more than 60 degrees electrical phase? That is a great question. It has happened. I will check it in simulation. I tend to not get too worked up about it in the simulation until I actually see what the finished speaker is with its crossover. If I know it's going to be an active box, I will start looking at that. So let's look at this box and see where it is. Curves, max output level system. Where is electrical impedance? And then the phase is up here. Okay, so this box, its electrical impedance is here, and the phase plot isn't particularly handy because, yeah. So see, this one's fairly well behaved. Minus 50 to plus 50. So there's also, do I recommend... Boy, the questions are coming in fast. Got to go fast. If it's more than 50, 45, 50, I actually start to worry about sort of older, lower cost, less stable amplifiers. And what you can typically do is when you start putting stuffing in this box, the impedance peaks will start to drop, and the phase swings aren't bad enough, or reduce as well, right? The phase swings wildly when these peaks are very narrow. Okay, as they sort of spread out, then the way the math works out on this is that the impedance is not going to swing as wildly. The other thing you can do is just totally freaking cheat and put like a 25 ohm resistor in parallel with the input of the box. Make it a big, powerful one so that it doesn't get too hot inside the box. But you can literally just put a 25 or 30 ohm resistor, and that lowers those peaks down. Doesn't really do anything to the bottom end of the curve because it's such a high value. And you can start to bring that, that impedance back into alignment, right? You don't have as much wiggle room. I did a design with a BNC coax 5-inch woofer where I had to do that. There's a RC network basically as a Zobel just to keep sort of less competent amplifiers happier. It's rare. I've only had to do that a couple of times. You have to work hard to get that. Let's see. Electrical phase, low QES drivers. Yeah, it really is. I mean, what is there is the RM Cantus 5-inch woofer has like a QTS of like 0.2. BNC has some, and they're amazing woofers. DS series. Go look at Bennett Prescott's videos on YouTube talking about the DS series woofers. The DS 115, both 15-inch and 18-inch woofers are amazing. They will crush you. I mean, just destroy you. But they're kind of a wonky thing to design around because their QTS is like 0.17. VAS is tiny for a woofer that big, and the BL is up near 40. And so you basically, I did a double 15 box where the port volume ended up being higher than the quote unquote rear volume for the woofer. And it's at that point, that's a definite don't for standard TL small modeling because these models start to break down when you're at those sorts of extremes. That's you gotta be careful with those. I actually did a bunch of modeling in horn response on that one. Instead of just trying to do it as a vented box, and I treated it more as a transmission line / reverse tapering horn to get that one done. And it came out pretty close, but the agreement wasn't as great as I would have liked, and I had to make a couple of tweaks. Let's see. Also, do the recommended box recommendation. I typically play with it until I get what I want. Like if I did the recommended box for this Vital Pro woofer, right? If I did that, what is it? It gives you a design suggestion. Yeah, see, it doesn't really want to give you, it doesn't really want to put it in a vented box. It's for the Omen. Yeah, it really doesn't. So if I used it, it would give me something way up here. And that driver has more than enough oomph behind it to put it in the vented box that I put it into. That's why, again, I stopped looking at like the named alignments, the QB3s and the BB4s and the whatever you want to call them, because in the real world, that alignment is not what you're listening to in the room. If you back when those alignments were developed, they were developed so that you could easily come up with your box size and port tuning frequency from tables. You didn't have to have the software and things like that. And now that we have the software and it's so easy to use that I just ignore those. Daniel, you missed the universe, answers to life, the universe, and everything. Boy, I need to catch up. Is it large front baffle close to the driver? Whichever you'd like, as long as you're willing to deal with the trade-offs for that. I have a great paper on that for the rule breakers, which were a very wide baffle, and why I did that. Let's see. For digital, let's see. Kind of hard. Yeah, speaker crossover design is like a whole nother ball of wax. Like that's a whole nother thing. I'm going to have to come back to this thread. You guys have started an entire thread, and I'm not going to sit here and make everybody watch me read it, which is awesome. Yeah, it's close to 100 degrees Fahrenheit here today. So it's hot. It was we had a high of 57 degrees Fahrenheit 2 weeks ago, and then summer came roaring back. So yeah. One of these days I will do a ground plane measurement outside, and I will show you how to do that. But it's got to be it's got to be nicer weather. It's actually almost let's see what is I can do distances pretty well, but I can't. It's almost 29 degrees in the room that I'm sitting in right now because it's not air conditioned. 29 degrees Celsius, 80 degrees, 84 degrees Fahrenheit, something like that. Let's see. Saraf, that is a perfect application for a passive radiator. That's where you gotta start looking at that, or understand, or take a real close look at how loud you're going to be playing it and see how tiny of a port you can get away with. So yeah. What else? What else do I want to talk about? I've gone over sort of the whole thing. Should I just put another driver in? Saraf, what's that 5-inch mid bass you're looking at? What is the driver? I'll go put it in and we'll play. We'll see what I come up with and what I'm willing to do with that driver. How's that sound? Does that sound like a good next step? Daniel, go for it. Ask something. SB15 NRX. Oh, I love that driver. I have not. I've used. I love that series. I've not used the 15 NRX, but I love that series. They sound great. SB15 NRX 30-8. We'll go to the Matasound site. What? They changed their page. 15 NR. Oh, NRXC. Is this the 8 ohm version? Come on. No, that's the 4 ohm. Come on. You can do it. This is entertaining. Oh, they've got the... Oh, it's discontinued. I see that. They've got the 2. How different is the 2 versus the... Will you cover driver FS in relation to port PR tuning? That is a great question. No, because I almost never look at that. I only look at that maximum output and input power and port velocity. So I don't really look at it. If I'm just starting a design, I will often sort of put the speaker in a box around its VAS and then port it at around its FS and then start moving things around from there. I don't pay attention particularly. And like there's all sorts of rules about make sure the impedance peaks are the same. Again, if you push these drivers hard enough, you've deviated from that anyway, so you're not going to see that same response. So I don't put a whole lot into a lot of those rules of thumb. I sort of learn where I can play with this software and when it's going to give me an answer that's reasonable. So let's take my face off here again. All right. We're gonna have to do an eye checker. All right. All right. So we're going to delete. Nope. No. Delete. No. Delete. save some curves here, or remove some curves here, because this is getting too confusing even for me to keep track of everything. All right, so we've got a new system. We're going to put this driver in here. Since I'm typing this in for the first time, we'll do it right. 15 NRX2C 30-8-5 FS 36.5 Hertz. VAS 20 liters. SD 82 whopping square centimeters. I chuckle because I'm used to typing like 1200 these days. Most of the stuff I'm doing is big pro PA stuff. Force factor 5.75. RE is 5.9 ohms. Something is not right. We've got QTS 0.34. Okay, now everything agrees. LE, and this is where the SP stuff is typically awesome. Yeah, 0.14 millihenries. Look at that. Xmax, 5 millimeter Xmax, and a power handling for this driver of, where is it? 50 watts. Okay. All right, so save. I'm going to save the driver, so in case I need to use it later, might as well. And now we're going to go to box. Okay. We're going to go click the design suggestion just to see what it does for us. We'll go back to this one. Apply. Oops. Okay. So remember what I said. So I've just used the design suggestion to give me a start for the thing. A lot of times, as I said, I will go to the box, the VAS. So this was what, 20 liters, if I remember correctly. Do I remember correctly? Yeah, 20 liters. And then a vent at the FS of the driver. And that's typically just where I start. Okay, it's not because that's good. It just it's convenient and easy, right? Vent. So let's take these curves again. I'm watching the system response. I don't know if I really care about the driver response or the vent response, or frankly even the electrical impedance, but I do care about maximum output level, and I care about cone excursion, and I care about vent velocity. Those are the things that I care about, right? And so what I'm going to do is, since that's the default system, I'm going to make a copy of it, and I'm going to start playing here and tell you what I'm sort of looking at while I do this. Okay. Let's see. Hi-Fi extremists tune their drivers down to 7. Nobody cares as long as. I don't know if I've seen things tuned to 7 hertz. I have seen some very how shall I put this, dubious port aspect ratios, things that are really skinny and really wide, and those are interesting because at low, they're basically dynamic equalization. At low volume, they'll be they'll aid the port, they'll aid the base output of the system, and then at higher volume, very quickly they close off, and the system becomes sealed. So you have sort of a protection against overexcursion at the same time as you have some dynamic equalization, and people seem to like it a lot. And I don't know why, because I don't find it particularly accurate, but maybe that's just me, and I'm an old guy yelling "Get off my lawn" for speaker design. In response to finally getting to watch one of these kind of live, in response to your first question, I can hear you. Thanks, Abe. Thank you very much. I appreciate it. Next time you're in Texas, let's have more brisket and whiskey, okay? Assuming this whole disease thing is done. Let's go for that. So for this driver, let's get back to this one. I'm going to start changing this box some. So I'm going to make it a little bit smaller. 16 liters, not that much smaller. 16 liters, and I'm going to tune it a little higher. Okay. Rename starting point. Curves, appearance, maximum output level. Okay. System response. We're going to go dotted. No, it won't. Okay. Change color. We'll change the color to something. Oh, we're already using red. Let's go green. It's hideous, but we'll see it. Okay. So the black line and the black line and the thinner black line are that initial starting point that I had for this driver, right? The green line and this gray line are maximum output. Oh, and I need to double check something. This gets me every time. Ha ha. Ha ha. Yep. We need to change those to 17. 10 meters per second is absolute silent port. Very low distortion, very little compression. But it's too restrictive for most drivers. Okay. So if I'm changing this new system, notice how that if I give it a slightly smaller volume and tune it slightly higher, I actually give myself a lot more maximum output for a curve that's really not all that different here. You lose the marketing cachet of being able to say I've got a F3 way down low, right? But where it counts, 40, 50, 60 hertz, where there's a lot more musical information, you actually have quite a bit more output in your system. Okay, so this might be something that I would, people went full mental, 15 kilowatt. Oh yeah, I've seen those. Oh, I know what you're talking about. Yeah, I know what you're talking about now. Yeah. I mean, I've gone full mental in my garage. I have 600 pounds of, horn subwoofers sitting behind me. There's nothing, and a 14,000 watt amplifier sitting there for them. There's nothing about that is not full mental. And my neighbors think so too. And my wife is the most wonderful person in the world because she puts up with it. And if she ever watches one of these, she's going to be saying, "What do you want now?" So yeah. How do I take into account room gain when I'm doing this? Brisket whiskey is brisky. Brisky. I'm all for it. And once we can gather again and do brisky together and listen to speakers, let's go do brisky and listen to speakers. How do I take account the room gain when you're doing to this? I don't on this program. I have done it in the past with other software, like Sound Easy has some finite element modeling. You can apply some general. I think this one has a. Where is it? Slinkwitz transform? No, because this will do, and that's again one of these. Room gain. It will enable room gain. So this one has a basic room gain feature. I don't know how much I really trust it because rooms can be there's room gain and there's room nodes, and a lot of times these things sort of run into each other, and so this is an answer that isn't based a lot in reality. You're not gonna find this room unless you do something, and this response unless you go to heroic effort. So I just tend to look at the overall response of the driver, and as long as you're not doing super weird things, and yeah, it does look like a basic pi quad. They're just putting basic filters on this, right? As long as you're not getting really weird shapes for the thing, your speaker, you'll probably be able to find a position if you move the speaker around to get a reasonable response. Like I have built hundreds and hundreds of speakers at this point, and you know what? I should define what I talk about when I say reasonable shape. Let's make an unreasonable box. Okay. Here is one example of an unreasonable box. That is an unreasonable box. When you see that much peaking for your subwoofer, that's going to be pretty one-notey. All right. I don't know if I would, and you see people build stuff like this on a fairly regular basis. In fact, there's a lot of commercial speakers that because they need to be made super tiny, they'll tune them way too high and they'll put them in a tiny box, and you end up with a big 60 hertz boost like this. I find that really annoying, and I can spot them in an instant when you're someplace. Each room, oh yeah, Rob, each room changes that. And not only that, where you are in the room, it's different. So it's really hard. That's why I don't pay too much attention to it when I'm doing the speaker part of it, right? Let's make a different box that's really bad for this one, right? So let's go down to 20 hertz and make this box twice as large, 40 liters, okay? Now, looking at this, you say, wow, I'm getting 20 hertz out of a 5-inch woofer. No, you're not. Your maximum output is way low. You have no power handling capability in your 30, 40 hertz range. You're going to hit that excursion limit so fast, it's not even funny. So these are sorts of things that aren't reasonable. So let's go back to trying to make a real box out of this thing. 16 vent of 40. What did I vent it at? Or yeah. So 40 hertz. So now I've got a 16 liter box that I'm supposed to try and fit a what is that? Like 7.5 inch long port, 2 inches in diameter. I mean, it could be done. You'd have to work on that, right? And if you're gonna put a bend in that port, go to your speaker port store, i.e. the plumbing store, and get the PVC swoop that's long. Don't make it be the one that's the right angle, right? Because that'll cut your output by a lot. Room gain will change that though. Yes, room gain will change that, Brian. But still, it's been my experience where when I have built speakers like that, and I have actually, right? They sound great up until the point that they don't, because you have so low power handling that all that extension sort of leads you to believe you can just keep kind of turning it up, and then all of a sudden the thing falls apart on you. It's not one of my favorite types of designs. So small subtle changes that see how I've changed from the one that was recommended. I've made it slightly smaller and tuned it slightly higher. I've actually got more max output in this region. It's still a nice smoothish looking curve here. I have no doubt you could integrate that into a room. You're still going to have to be juggling this port diameter. Like if I made this a 75 millimeter port, right? See how much more maximum output I have? But now I've got a port length that's almost half a meter long. There's no way I'm going to fit that in a 16 liter box, right? There's just no way that's not going to fit. So that's a non-reasonable thing to assume. And if I make the port way too tiny, and you see this all the time, let's make that a 1-inch diameter port. See what I do to my maximum output? My maximum output plummets. Okay. It's very easy to get the port in the box. The port is now only 1.5 inches long, right? But you have no output at high volume. What do I think of PA clones, like L-acoustic clones? I'm not real fond of the clone stuff just because of the intellectual property issues involved with that, and people trying to make a living on that. I have had designs of mine stolen, and that is not fun. It's not cool. There is very often, depending on which entities you get these things from, a level of quality control and consistency from unit to unit that is missing. And in other ways, you can see things that are spectacular. I have ordered things from some of the factories that are the fit and finish is immaculate, as good as anything you'll ever see. And so it just varies wildly. They weren't clones; they were their own independent products. They were obviously designed to compete with, say, for instance, in this case, it was an amplifier. It was a CVR amplifier, and it was designed to compete with PowerSoft. But it is not a clone. It is not a lookalike copy. So you want a smooth bend, not a sharp bend. Let's see. Yes, you can use an L knee so you can hit 29 centimeters, but you want that bend to be a long swoop. You want it to have a long radius to it. You don't want it to go 90 degrees, okay, or even a short radius. If you're in a plumbing store in the United States and you ask for a swoop, what you want is, and this is a super long one. This is is you want something that has this longer bend to it. You don't want PVC elbow 3-inch. You don't these short. You definitely don't want this one, right? Like this one or this one is not a good idea. This one's a better idea. This one will work. In fact, I've used this exact one from Home Depot on many occasions. But this one's a really bad idea. Let's see. Can I talk about K-factor? That's going to have to be a whole nother video. That's yeah. There's end corrections. There's K-factors. There's end corrections to the port if the port has a radius to it, just for the end versus the entire port having sort of a smooth swoop. I've got to update my port paper because of that. Things like that. There's all kinds of stuff there. That's gonna be beyond the scope. Sorry. What's the effect though? If you use the short one, your port will probably drop half of its output or more. You'll have at least 3 dB less output. That you've got an air mass that's trying to travel back and forth, and the air mass doesn't want to bend quickly. And so by bending that air mass quickly, it basically forms a bunch of turbulence and roils up, and just rolls up on itself, and it does very bad things. I would violate copyright law if I pulled up a paper by Juha Bachmann. I think it's Bachmann. Who at the time was at university. I think it was his master's thesis, but for years was with Genelec, where he has a right angle in a port, and he has the compression chart there, and it's bad. Don't do it. Let's see what else we have. Boy, we have an active chat today. We still have a bunch of viewers, and I am way over time. My wife is going to kill me. We'll go like 3-4 more minutes, maybe 5. Then I've got to get offline. I had no idea that we were this far past. Any other questions now that I'm showing you a Google search for PVC fittings? This is the greatest live stream ever. We'll go back to pictures of nice woofers. How about that? That's better. Crash, I would even say, and this is a port paper that I'm doing hopefully soon. It would add more chuffing, Rob. Reef, the recording will be available, so you can watch. Let's see. I would still say that even with a large port area, you're going to have a loss. I have done a very large PA system a couple of times, subwoofers, where I had to bend the ports, and my radius, my effective bend radius, was like 3x the port width to keep it low. And I actually have a tentative box design for the tour grade Eminence 18s, which I have sitting in boxes over there, where I'm going to do a port with a sharp angle and a long swoop, and have the port be boltable in. What I do for you folks, so that I can get a so I can show the losses for a real big version of that port. What's better, slotted port or circular port? Circular. Based on my testing, I did an entire port paper. Go to the DIYRM site, which you can't see because of the light-colored background. Maybe you will be able to now. Go to this webpage here, and you can find it. Circular port has the least losses. If the rectangular port has an aspect ratio of 3 to 1, so 3 width, 1 height, or better. So, you know, the more square-like, the better off you are based on my testing. I did a 10 to 1 and a 30 to 1, and they were bad. Triangular ports tend to be bad up in the corners of boxes, but sometimes you got to do them because there's no other place to put that port on the baffle, which is unfortunate, but that's just the way it goes sometimes. So yeah, I'm a big fan of round or low aspect ratio rectangular ports. How do you make a smooth curve with a slotted port? It is good enough to sort of approximate it, and this is one of the things, again, that if I had infinite time to build infinite options, I'd see how good enough it is. But you approximate it with miter steps. So you just got to get good at cutting miters on your table saw. Daniel, yes, kerf it. You could kerf it, and I'm actually looking at kerfing some ports in the near future. But that is a level. That is also a level of dedication. 1/3 of cone area. What's that? Do we generally believe that with the Dayton doohickey? Okay, that's a great question, Greg. Yes, no, maybe. I believe them for the voltage drive level of the doohickey. You're talking DATs, right? Them at that drive level. The problem is very few times that drive level is so tiny that you know, very rarely do you use a speaker there. I don't even know what voltage level that thing puts out. I haven't bought one or purchased one, but I have a paper on measuring teal small parameters over a variety of different voltages. I did it with a VIFA TC woofer, which are no longer available, but it was what I had to torture with the thing. And I have showed that very quickly you start to diverge, right? So what ends up happening is that people that use that device and they get different answers, it's because they're driving it at different voltage levels. If they actually stopped and put those parameters into a box, and I'm getting a message on streaming, so I'm going to kill my video. If we put those parameters into the box plan, you would actually see that the curves weren't all that different. In fact, so yeah, that's DATS V3. Yeah, I mean it's okay. It's not my favorite thing in the world. I don't own one. If that that tells you anything. I prefer to use custom jigs that I designed for REW or SoundEasy. I can do impedance measurements up to about 4,000 watts if I need to. So yeah. Let me see if I can find that port paper. again, great live video where I'm on a screen you can't see. That is awesome live video. I'm an entertainer. Okay, so if you go to my DIYRM page, you can, in fact, let me just do this on this screen. If you go to the DIYRM page, the pinned post is a spreadsheet of various papers that I've put out. And I have a white paper on Thiele Small, teal, oh, I did it again. And I have a white paper on, where's ports? I got a lot of them. Where's ports? Port nonlinearity testing. That's the other one. That probably comes in handy. And so what I've done here is for this one, wow, this was 3 years ago. I measured this driver at a variety of different drive levels. And then I did the, so I did 0.3 volts, which I think is probably in the range of where the DATS is. I don't know. I shouldn't say that because I honestly don't know. But I did this driver all the way from 0.3 volts to 6 volts. And you can see, you can watch the parameters start to shift. Like it starts at roughly 10 a VAS of 10 liters and ends up at a VAS of 16 liters. BL drops, right? MMS shifts for a variety of reasons, but we'll get into that. That's a whole nother thing. And if you start plotting the responses, right, you see where they are drastically different from the beginning to the end. But what people do is a lot of times is that they're measuring, let's say these 0.3, 0.5, 0.75, and they're like, oh my gosh, I got a FS of 55 hertz or 56 hertz, but the factory says 53, and oh my gosh, it's so different. No, it's not. Just plot them over each other. You'll see that it's sort of this area here where they're nearly identical. It's just not that big of a deal. The other one that I did was with the ports here. It shows where, yeah, so there, I made a bunch of ports. This is just a round port, right? Round port with round over, round port with straight, and if I go to the slotted port, see how this line, the slotted port line is below? That means you've lost port output, okay? It is just not as much output per input drive voltage level. And if you go to a 30-to-1 port, you lose even more, right? So these are it. This is why I'm not real fond of these rectangular slot ports. Yeah, Brian has all the measurements tools. Yeah, 4 kilowatt small signal. Yeah, I use the impedance, the one I've designed to do up to 4 kilowatts so that I can measure the impedance of the entire system. It was designed to tell me when horns, these big PA horns, are becoming completely non-modeled, right? So yeah. Alrighty, well, it is way past time. I expected this to only go an hour. It went over an hour and a half, it looks like. Thank you, everyone, for joining me today. I appreciate it. Hopefully this was entertaining and educational. I'm going to have to drink some water. I'm starting to lose my voice. But this has been great. I will do this again soon. I don't know if I'm going to be able to do one next weekend. We have some things going on where I may or may not be able to get around to one of these next weekend. But if we can, if you wanted to convert a vented box to closed box, what happens? Usually you lose a lot of low frequency output. And you can even, well, I shouldn't say that. I was going to say something that probably wasn't true, so I'll stop. But yeah, I wouldn't try and convert them. I mean, you can easily model it, right? You can see what the difference is between the two. But yeah, all right, everybody, have a good weekend, or what's left of it, and I will see everybody online. talk to you later. Bye.